What's up, guys? Before we begin, I'm going to show you how you can install BirchUtils, my library with the utility functions. So you can go to the repo and the latest version and download the zip file. So you unzip that file and then you just go into the directory and you run make. If you get an error like C2X is not available, you need to upgrade your GCC. And then you need to run sudo make install, enter your password. And if you get an error which says something like no such file or directory, that means that your library directory is wrong. In that case, you run ldd bin ls and you take this string right here. Then you edit your make file and you go to the lib directory and delete what's already here. And then you just paste this in and then you run sudo make install again. And you can test if BirchUtils worked by creating a C file where you include the BirchUtils.h. You create a simple main function where you declare an int8 variable like x and set it equal to 5, say, and then you return x. And you compile this by doing gcc ac-o, and then you add BirchUtils to the end. And if this compiles and runs, then everything is working. So let's begin our regular episode. Sup, guys? Welcome to today's show. So today I'm recording from my Windows machine, and we are going to continue our series of creating a virtual machine. I have made 3 episodes this far, and today we are going to focus on memory, virtual memory. So my goal for today, I'm not sure how far I'll get, but I want to implement 3 new instructions. So let's say we put a value inside of the AX register, 45 or whatever. And then inside of another register, BX in this case, we will put a memory address. So something like this, maybe. And then we are able to we move into that memory address the value of AX. So from AX, where we pick up the value, those brackets signal that we are not moving it to the BX register, we are moving it to the memory address inside of the BX register. So that's one thing, but I want to begin at another end by implementing the regular stack functions. So basically a stack works with 2 instructions, push and pop, like this. So let's say we have an image of the memory. So let's say here are the different code instructions, what is usually referred to as the .text segment. And then we have the stack, which is everything else, right here. And down here at the end, we have the highest possible memory address. And in a 16-bit system, that is FFFF. And at the top right here is the zeros. So basically, the stack is everything which is not the code segment. And this break line here is defined when we start our virtual machine. We will give it a couple of instructions to process, so we know how big this is. And we need to add protection, so this segment cannot be written to. So this should be read-only. We can add the permissions here. So this is read-only and executable. So that means we can put instructions there and let the CPU process them. On the other end, though, we have read-write, but not executable. All right, so the stack from the beginning is empty. So it looks like this, kind of. And let's say we will put something on the stack. So first we put it inside of a register. So we can put the value 45. And then we execute push AX in this case. So that means we are pushing the value inside of the AX register. When we are coding regular x86, it is possible to do stuff like this. But I will only support pushing a register, and only the general purpose ones, AX, BX, and so forth. All right, so if we push this value will be here. And all these values are 16-bit values. So, yeah, it's a 16-bit value, which means that the memory address to this 45 is this, but minus 2 bytes. So EC, which means we need to know where we are at the stack. And there we have a special register which is called SP, stack pointer, which begins at FFFF. So when we issue a push operation, we first decrease SP by 2. So from FF to FC, and then we copy the value into this address. So basically, this operation right here translates into move AX 45 sub SP2 and move into SBAX. I will not implement so you can use a move instruction to move into the SP register, but this is basically what's happening. And let's say we want to move push another value. So let's say we move into BX. We could reuse AX as well. And let's say we put the value, I don't know, 50,000. And we push BX. That means that this stack pointer will go to the FFFA, and this value will end up on top here. So this is the representation of the current stack. If we want to get this value, 50,000, what we can do is, let's say we have a lot of code, blah, blah, blah. We do a lot of stuff, and then we want to get this value back. Now we can pop it. So we pop into a register, let's say CX in this example. And this basically means that we take the value on the top of the stack, wherever the stack pointer is pointing towards, because the stack pointer is pointing to the top of the stack. So we take this value 50,000 and we put it back into the CX register. So we remove it from the stack. We copy it to the CX register and we increase the stack pointer by 2. And then we can, if we do this twice, we will take this 45 as well. This stack pointer will go back to where it was. Okay, it starts at FF, so it should have been D, not C, but never mind. And in this case, the 45 value will be copied into the CX register. So pretty simple instructions, but very powerful. Because when using these 3 methods of altering the memory, we can do everything with regards to memory. We have complete control over how the process's memory will look, and not only the process, the whole virtual machine RAM, basically. Okay, so let's see how we can implement this. Let's start with the push operation. All right, so let's see, where are we? VM prog system halted AX E flag set. Yes, in the last episode I implemented a function to make it a little bit easier to run code. Let's see how I did it. Right, I can write programs like this now. So I call this example program with the VM as an argument, and then I can use these I and I1 functions to give a list of instructions like this. So that makes stuff a little bit easier. Later on, perhaps in next episode, I'm gonna switch to using a compiler instead, to compile our assembly language into machine code. But that's the next step. All right, so a push operation. How to do this? Let's see. Yeah, we have these small functions with a double underscore in the beginning, one for each instruction, and all of them take a VM, an opcode, and possibly up to 2 arguments. All right, so let's see. I think I'm gonna implement this like this. So I just want to have one opcode for push operation. So basically the argument will define whether it's into the from the AX or the BX and so forth. So we should only be able to push 16-bit values, I think. Yeah. So either we should ignore these set higher and lower flags, or we should error out if they are set. Ignoring error silently is not really a good way to do stuff, I think. So let's error out in that case. So basically the argument will be either 0, 0, 0, 1, 1, 0, or 1, 1, depending on the AX, BX, CX, or DX register. And now I closed the wrong thing. Let's get our header file back. And I hope this is big enough for you. I think it should be. All right. So let's start by adding our instruction to our list of instructions. And yeah, this enum right here. So, well, let's put it on. I have reserved 18 and 19. So, which is the next one then? It's 1A, right? So I will set push equal to 1A and pop equal to 1B, like so. And we also need to define it in our instr map. And here we're going to tell the program how many bytes this instruction will be. So basically, push will be 2 bytes. Or 2 bytes, let's see. I mean 3 bytes. I don't think we want to have, because the move instruction takes 1 argument. Or why waste precious memory? Let's do 2. See what happens. Or do we need to recode everything? Yeah, we kind of do. Okay, let's do it like this. It's 1 byte extra. And then pop, and maybe we can add more features which utilizes 16-bit later on. So let's do it like this. Yeah, I don't know. Like this, maybe. Okay. Something like this, I guess. And now we need to create this little function, or I don't know if it's little or not. It's a void push, and it takes a VM opcode args a1 args a2, and let's also do pop, and let's create the function declarations as well. Or maybe I haven't done that yet for these functions. Maybe I should. So we have move. Do we have anything other? No, we don't. Alright, let's see if we can do this in an easy enough kind of way. So let's open a new one. No, that's not right. This is better. Alright, so let's see. We do not need this part. So 2dd, and you can do dot and dot and dot and dot and dot. Like so. And we also need to remove this stuff right here, and maybe we can do like this. Why is this? Right. Never mind. Yeah, something is wrong, actually, because these are both 3 characters long, but this is 1 character smaller. So what have I missed? Opcode, VM, args a1, right? Let's fix that inside of the C as well, so we don't forget. Right. And let's also remove the variable name. Let's just do this. Like so. We don't need this. And same with this argument right here. And with this one. Okay, it's starting to look kind of good. I also like to remove the spaces when I define function declarations for some reason. Probably pretty historical reasons. And let's also add this semicolon at the end. All right. I think this is right. VM opcode args. Yeah. Looks okay. So let's see, we do V and G and we copy. Or let's copy it the right way. 11DD. No. 11DD. And this should go inside of here. And we did have the move already, so let's not make duplicates. All right. Function declarations. Right. This we can close. So how do we do this pop operation? First of all, we need to check for this these flags, because if the higher flag or the lower flag is set, we want to error out. So basically we can do something like, we can do this. So if higher and lower, if higher or lower, then we error out. It's good. We can put this inside of our pop as well. Okay, we don't need to switch for the opcode. What we do need to check is if the stack pointer is pointing towards the lowest of addresses. Because if it's like 0001 or 00, we can't really decrease it by 2. So in that case, we will also error out. And let's see how we do this. We have a couple of macros, I believe. So we can probably do, maybe I should check. VM, EX, all right. So if VM stack pointer is less than 2, we will error. And same here actually, but the other way around. So if the stack pointer is more than D, then we'll error out. Okay. So let's switch on the argument. A1. And we will have 4 different cases. So basically we will have 00, which will be this. And this is push AX, like so. So let's copy this down. 1, 2, 3, 4. And this will be the bx with 0, 1. And then we have the cx with 1, 0. And we have the dx with 1, 1. So these are our three possible combinations. And if we get anything other than that, we will error. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. So let's do int16 source. And in this case, we'll set the source equal to the VM's AX register. And then we have BX, CX, and DX. And if we get all the way down here, past the switch statement, all we need to do is we take the VM's SP and we decrease it by 2. But before that, we need to check that we are in the right domain, that we are not trying to, let's see. No, never mind. No, do mind actually. If the stack pointer is pointing towards the code segment and we try to push something onto it, that should not be allowed. So let's check this in the beginning. So if the VM's stack pointer is less than and we need to check it against the break line. Let's see what we did call that. Alright, it's just a B inside of the VM. So if it's less than the VM's B, but not just the VMB, because we are gonna decrease the stack pointer by 2 and then push something into it, which means we need to compare this to the B minus 2. Like so. But what if the break line is at position 1? What happens then? So we need to have one additional check. So this is one thing. And we need to check that if the VM's break line is more than 1, and this. then we error. Otherwise, we're fine, I guess. Let's see. So what if it's not more than 1? What if the break line is at 0? It probably won't be, but if B I think we don't need to overcomplicate things, actually. Let's do this for now and have a mental reminder that we might fix this later on. So we are out VM, and this should be a seg fault. If we try to write to the code segment. Alright, so we decrease the stack pointer. And then we copy the value into that position, which means we need to do a little bit of pointer arithmetics, right? Let's see. Yeah, so let's create an int16 destination. Or maybe it's easier if we do like this. We make this a void pointer. Set destination equal to the VM's memory plus the current value of the stack pointer. That should be the right thing. And then we will just set this. No, we need to have this, I suppose. And then we set that equal to the value of source. And that's it, I think. I think we covered all the different angles right there. And basically I think we can copy a lot of this stuff when we do the pop, because it's basically just the reverse, right? So let's put this in here. We can let's do this. Nope, not that. This. And this we already have. If SP is less than 2, this should be gone. What about this, the break line? When we are popping, we are only reading. And we should be able to read all segments, so we can remove this entirely. And I think we need to make this a pointer and this a regular thing. This should be the destination instead. And we can use the same values. Alright, so in this case we want to increase the stack pointer by 2. And we want to set the source equal to the memory plus the stack pointer. And then we'll set the source. No. Let's see. No, we can't do like that. We need to actually change it inside of the switch statement. So let's take this and put it before the switch. This we still need. But not this. And not this. And in this case we don't just want to set the destination variable. What we want to do is we want to take the AX and set it to the value at the source position. Right. So we have BX, we have CX, and we have DX. Great. All right, and we need to make it call the right function. So let's see, exec instruction. We switch on the size, and then on the instruction. So if we have a push, we want to call the push function, and we'll send our VM, we will send our opcode, our arg A1 and A2, and then we'll break. And same with the pop operation. Something like this, I guess. Should go one more step, like so. And how can we verify that this works or not? What are we currently doing? We are checking the value of AX. We can still do that. The flags we can keep, doesn't matter. But we do want to show the contents of the memory, basically. So let's do something like, let's first find where we are printing the stuff. Where is it? I always seem to be looking for that. So if you search for E flag, here it is. Alright, so let's bookmark this part so we can find it easier. And if you don't have this feature, I can recommend it. It's very good to be able to highlight parts of your code and keep it saved like that. If we go to the JSON preferences, what we need to add are these 3 lines. So basically we decide what kind of background color we want for the bookmarks. And then we just need to install an extension which is called bookmark, I think. How do I see if I have installed it already? This one. So it should be the one that says bookmark version 13 by Alessandro Fragnini. If you just install this thing and add those 3 lines, then you can just do Control B at any line in the code, and it will highlight it. Maybe you need to add the key binding yourself, but I think the default is Control B. Or maybe not. So add the add the key binding. All right, where were we? Yes. Maybe I should highlight this instead. All right, so when the system is halted, we want to print this stuff, and then I want to print a part of the memory. So let's do print hex, and I want to take the VM's memory plus FFFF, and let's print 64 bytes. So minus 64, and we want to print 64, and we don't need any separator. And print hex is a part of the BirchUtils library. If you don't have it, you can grab it from this repo. This one. So let's save, and let's see if I have any errors in my code. So we make clean, jump down a little bit. Let's also set the home to this. Clear the screen, run make, and boom. Okay, not as much as I feared. Assignment 2 and 16 star, blah, 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 from incompatible pointer typing. These kind of warnings when we come to the topic of pointer arithmetics is pretty new in the side of GDB. It has been here for a couple of years, and it's very annoying, I think. Because as a programmer, if I do some pointer arithmetics, I probably know what I'm doing. Otherwise, I wouldn't go into that topic at all. So this is not even a warning. These are errors. So it doesn't compile because of this stuff which should be totally allowed. But it's not, so what can you do? Well, we need to go over the water for water, which is a Swedish proverb. So let's do a void mem, and let's set mem equal to this. We set dest equal to mem, and then we can do this. Pretty annoying. And we need to do something similar here, I suppose. So we do a void mem, and we'll set mem equal to this and source equal to mem. And now it compiles. So basically, it's just some kind of protection so you don't do the wrong thing, but I do not like it. Okay, so if we just run this now, this is a copy of how our memory is looking. 64 bytes, maybe 64 is a little too much. Let's do 32 instead. So this is the 32 bytes of memory in hexadecimal numbers, which has the highest memory addresses. So basically, if we push stuff, it should end up at the end right here. So let's push stuff. If we go to our main, we can just add, let's see, we have 4 inside of AX. So we should be able to do something like, let's see, I1. So I1. And we want to give it a push, and the argument should be 0 for AX, which means that we should move a 4 inside of the stack. Let's also print the stack pointer at the end. So now we can just scroll until we see red. And we can add a line where SP is equal to SP, like so. Too many arguments to function I, okay. I1, move, I1. I is around, no, that's not it either. Let's see. So we have I0 right here, STE, and then we have I around it. And we have I1, too many arguments to function I. I misplaced the parentheses. This is right, I think. Okay, now it compiled. So let's see what happens. Okay. That's not what I anticipated. SP is equal to 0. And we do not get anything in the memory. That's a little weird. Why is SP 0? Let's see if it's 0 even though we don't give this instruction. Yes, it's still 0. Okay. So let's see when we initialize the virtual machine. I think we have a function just called virtual machine, yes. And this just zeroes out everything. But the SP should start at the highest possible address. So we take, let's see, we take PSP and set it to FFFF, like so. Okay, so now it's set to this. If we go back to our main and we uncomment the stuff, let's see if it affects the memory somehow. No, it did not. It certainly did not. Push 0, 0. And if we go to push, we did not get an error from this one. And we switch on A1, which means that we should set our source to the value of AX. And we decrease the stack pointer. And it did not even decrease, did it? No. So this is probably not called. So let's see. Exec instruction. Case push. We call it push. Ah, now I get it. I think I do actually. Yeah, we give the halt instruction and then this. But everything stops with the halt instruction. So that's a little bit lame. So this should be better. Right, let's try again. Okay. All these parentheses. So here we have this and this. and this and this. We have halt. We have this should be gone. So let's try this again. Okay, now stuff's happening. The SB has decreased by 2 as we wanted it. And the memory is looking a little bit differently. Now we have a 4 right there. Do we want that 4 in this position? Or do we want it here? I think we can live with this actually. Which basically turns our virtual machine into a high byte order machine. Which is kind of okay. Let's see if we can do the other way. If we set the AX to 2 instead of 4, no, we can't do that. Let's set it to 4, let's push, and let's set another register. Let's see. Move 04. Where do we have the different move? Right, so 03. Then I suppose, no, I'm looking at this the wrong way. 09 should be moving into the BX register. So let's do that. Into BX, we should move the value. Let's do, I don't know, 5005. And then we want to pop. So we'll do I1 pop, and the argument will be this is AX, this is BX. So basically, we first set it to this number, and then we try to pop into that register. So if this works, the memory should be unaffected. The stack pointer should be FFFF, and this BX register should hold this value. Yeah. So let's see, where were we? Let's print out the BX as well. like so. Oh, all these parentheses. So we have one here, we should have one more right here. Alright, let's see what we get. Bx is 0e00. 0e00. 0e. It's 14 instead of what we had. That's a little bit weird. 14. What if we don't do the pop operation? Then we have this value that we set. But where does it get this 0e value from? Weird number. So let's revisit the pop. And we increase. We should copy and then increase. Right. Otherwise, it's not correct. So let's see if we get a 4 this time. We do. Pretty nice. And as you can see, this is still on a stack because we never delete stuff from memory. But since we have reset the stack pointer, we will overwrite this the next time we push stuff. So this is working exactly as we intended it to. Took a little bit longer than I anticipated, but it worked just fine. So we will have to wait a little bit with the move into memory instruction. Alright, so what have we learned today? We have learned how to create a push and a pop operation and handle memory, a virtual stack. And I hope you liked this episode. And don't forget to like and subscribe, because there will be more in this series and others. And thanks for watching. Thanks for today.